Hey guys, this is Unit 3 Notes B. Today we're going to focus on covalent bonding. Opposite from an ionic bond where we actually transfer, gain, and lose electrons, these electrons are shared between the atoms that are in a bond. So covalent bond is all about sharing. So covalent bonds are going to occur between two or more nonmetals. It's not metal and nonmetal. We're not balancing charges anymore. We're all the way on the right side of the periodic table, on the other side of that stair-step line, only dealing with nonmetals. Means we don't have to worry about polyatomic ions either. The difference between what happens in the bond is we're sharing electrons as opposed to transferring electrons as we did with the ionic bonds. So when we share electrons, that's going to allow each atom to have access to the number of electrons that it needs in order to complete its octet. So we're still trying to achieve the octet rule, but this time, instead of gaining and losing, they're going to share. So there are three main types of covalent bonds. We could have single bonds, which would share 2 electrons. We could have double bonds, which could share 4 electrons, 2 in each. And then we could have triple bonds, which could share 6 electrons, 2 in each of the 3, 4, 6 electrons. So we could have single, double, or triple bond. A single bond would be represented with a single line. So an example of an atom, or I should say a molecule that has a single bond would be hydrogen. Diatomic hydrogen would share just a pair of 2 electrons, and they would share between. As it turns out, hydrogen only needs 2 electrons for its octet since it only has the 1 s orbital. So this is going to complete the octet for both hydrogens, allowing it to share. An example of an atom with a double bond would be oxygen. So oxygen would then share not just 2, but 4 electrons. Those 4 electrons will complete the octet for each oxygen, but to get the total octet, each oxygen would also need 2 lone pairs. So we're going to draw the dots to represent the lone pairs. The first thing you should know about lone pairs is they always come as a pair. You're never going to separate your dots. These aren't single atom Lewis structures anymore. These are now for molecules. So molecules always just have either bonds or lone pairs, never a single electron alone. We want the total number of electrons and bonds, lone pair electrons and bonded electrons to equal 8. So for each oxygen, we have 1, 2, 3, 4. And then each oxygen also has access to the 4 in the double bond. So 4 and 4 would give 8. Same thing happens over here to this oxygen. It has 4 of its own, plus the access to the 4 shared, so also having access to 8. So these bonded electrons are kind of doing double duty. They're completing the octet for both atoms. A triple bond is going to be found in nitrogen. So with nitrogen, we're sharing 6 electrons. So those 6 electrons count for each nitrogen, but we would still need 2 more in order for each nitrogen to have 8. So for each nitrogen, we have 1, 2, plus the 6, and then 1, 2, plus the 6. So we have an octet available for every single atom on the board, just it may need to share different numbers of electrons. We're going to figure out we are going to go over how to determine whether it's single, double, or triple. It all has to do with the number of valence electrons that the atoms bring in the first place. All right, so let's go over some more examples of Lewis structures. I actually kind of did hydrogen already with the single bond. And then hydrogen does not get lone pairs around it because it only has the 1 s orbital. It's an exception to the octet rule, more like a duet rule. It only needs 2, which each have access to with that single bond. So let's move on to CCl4. We're going to put the carbon in the middle and the chlorine around it. Molecules tend to bunch like flowers instead of going out straight in a line. So we're going to put the carbon in the middle and then attach that to chlorine on every side. The next question is, how many lone pairs or how many dots need to go on these atoms? So carbon has access to 4 separate single bonds. Each single bond has 2 electrons. So if I have 2 4 times, I've already met my octet. That's going to be 8 electrons. But let's look at the chlorines. Chlorine only has access to 1 single bond. So that would be 2 electrons. it would still need 6 more to get up to 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And that, of course, will be the same for all of the chlorines. So that would be our Lewis structure for the carbon tetrachloride, having 6 electrons or 3 lone pairs on each chlorine and having the single bonds. Now let's try nitrogen. So if you remember, this had a different type of bond. So how did I know that? So I'm going to come up here so you can see this a little better. Nitrogen, let's just sketch it out with a single bond and see what the problem is. If I had a single bond, that would be 2 electrons, and then each nitrogen would need 6 dots around it, or 3 lone pairs, because 6 plus 2 is 8. So in order to give both nitrogens an octet, I would need 6 electrons plus the 2 shared. That's just the sketch of a Lewis structure, only being worried about the octet. But here's the problem. How many valence electrons does nitrogen have? Well, since it's in column 15, it would only have 5 valence electrons. Each of them would only have 5 valence electrons. So I can only have 10 electrons in this structure. But how many do I have drawn right now? 2, 4, 6, 8, 10, 12, 14. If I only have 10 electrons, then my structure can't have 14 electrons. The valence electrons are basically your budget. So now how can I get an octet with only 10 electrons? And the answer is we need to share some more. Whenever you share, you're going to replace 2 lone pairs, 1 on each atom, with a shared pair. So that still keeps my octet, 4 plus 4, 8 electrons, but it does it with less total electrons, 2, 4, 6, 8, 10, 12. So it's a little bit better, but still not quite enough. So I'm going to take away another pair and share even more. Now I have 2, 4 plus the 6 is 10. So I've met my budget. That budget, that number of valence electrons, is what's going to drive this single, double, or triple bond in the middle. We have to figure out how to get them each access to 8 electrons, but with the number of valence electrons that there are. So this would be my answer for the nitrogen. Triple bond, lone pair on each side. Now let's work on the hydrobromic acid over here, HBr. So here I'm going to sketch out. You kind of always want to start with just a connection. You know, you need at least a single bond in a covalent molecule. Now hydrogen wants access to how many electrons to complete its octet? That's the one that's special, where you only want 2 electrons instead of the 8. So hydrogen already has access to the 2 in the single bond, but bromine wants 8. And with it only having access to 2, it's going to want 6 more. So we will surround bromine with single bond, or with single electrons around, the 3 lone pairs. Now, how many valence electrons did hydrogen have? Since it's on group 1 on the periodic table, it only has 1 valence electron. Bromine, being in the halogens, would have 7 valence electrons. So that means that I want my structure to have 8 valence electrons. 2, 4, 6, 8. So we've met our budget, and we've completed our octet. Hydrogen is happy with 2, and bromine has 2, 4, 6, 8 that it can get access to, so it has a complete octet as well. So there's our structure for the HBr. Let's move on to the O2. Again, I'll sketch it with a single bond in the middle. And I know that if this counts for 2, I need 6 more on each. So this is a good starting point, but we've got to check our valence electrons. How many valence electrons does oxygen bring in? Well, since it's in the 16th column, it has 6 valence electrons. So 6 plus 6 is 12. Does that structure have 12 valence electrons? 2, 4, 6, 8, 10, 12, 14. Too many. We've overspent our budget. So the solution is more sharing. Get rid of the lone pairs, replace with a bonded pair. Get rid of 2 lone pairs in favor of a bonded pair, because a bonded pair can do double duty. Now I have 2, 4, 6, 8, 10, 12. I've met my budget. And I've met my octet. 2, 4, plus the 4 in here is 8. And then 2, 4, plus the 4 in the double bond, 8 for the other oxygen as well. Last one, carbon monoxide. Again, I'm going to start with a sketch. And since I have to have at least one single bond, I would have then 6 more electrons on each one in order to complete the octet. But we've got to check the budget. How many valence electrons does carbon have? Well, group 14 would have 4. And then oxygen, as we said, has 6. So that's 10 electrons. How many did we draw? 2, 4, 6, 8, 10, 12, 14. Too many. So we need to share some more. Get rid of 2 lone pairs for a bonded pair. That's going to get me down to 2, 4, 6, 8, 10, 12. Still not enough to meet the 10 budget. So I'm going to get rid of 2 more lone pairs for even more sharing. So I end up with a triple bond again. 2 plus 6 is 8. The other 2, 10. So I've met my octet. Notice how the nitrogen had 10 valence electrons and it ended up with the triple bond. And the carbon monoxide also had 10 valence electrons and ended up with the triple bond. So it doesn't matter who brings in what electrons. All the electrons go into the budget, and then you have to make sure the total structure is representative of that number of valence electrons. So some people get caught up on, well, the hydrogen was only supposed to have 1 or the chlorine was only supposed to have 7. Once they're bonded, like you're in the marriage, it's all community property. And so then it's going to get spread out through the molecule. It doesn't matter who brought in what electrons. So 10 valence electrons ends up with the same structure, the triple bond. All right, so that's our first experience with covalent bonding and drawing Lewis structures. This is a huge part of what you're going to be tested on in Unit 3, being able to determine the type of bonding in different molecules, and then making sure that it's a complete octet for every atom. Another mistake I see sometimes is people trying to put dots in the same place as a line. That never happens. Think of the atoms as having 4 corners, and on every corner you can either have bond or lone pairs. And then keep your electron dots as pairs. All right. So what we were doing there, where we kept making sure everything had 8, was again following the octet rule. Covalent bonds do it a little differently than ionic bonds. Instead of transferring, they actually have that shared 1, 2, or 3 bonds that are going to share in order to allow them to have access to the 8 electrons. And why do they want the 8 electrons? Because they want to be like the noble gases. All right, so that was a little bit of problem solving, right? Back and forth. There actually is a way to calculate the type of bond that you need. So I know this looks a little bit long, but it's actually not as hard as it seems. Just like we started with the last one, we're going to sketch a skeleton. So I'm going to do an example of carbon monoxide, which was the last one that we did. So we're going to sketch the skeleton, CO. And then this is referring to putting carbon in the center and letting the molecule kind of be a flower where there's a center and the molecules go around it. So it's the same thing I was telling you about with the structure before, right? Here's the calculation part. First, we're going to calculate how many valence electrons the atoms would need in order to complete the octet. It doesn't matter anything else about how many valence electrons. They just want to know how many electrons are needed for an octet. So for every atom on the periodic table, except for hydrogen, that would be 8. But hydrogen, only having a 1s orbital, only needs 2. So the N equals 8 for all but the hydrogen, and for hydrogen, it would equal 2. So that is specifically for the needed. So for carbon, it would need 8, and for oxygen, it would need 8, because they're not hydrogen. So N equals 8 plus 8, which is 16. Now we're going to calculate what's available. What's available is your valence electrons. So this is basically what I was calling the budget before. How many electrons are we working with? So for carbon being in group 14, it's 4, and for oxygen being in group 16, it's 6. So I now have a total of 10 electrons available. The next thing that I want to do is to find the difference. What is the difference between how many I would need in a perfect world and how many I really have to work with? So it's just subtraction. S for shared, S for subtraction. This gives me 6 electrons. What that means is I'm going to have 6 electrons in bonds, 6 shared electrons. So now we're going to put those shared electrons in as a bond. I already have 2 electrons in this. So if I put a double bond, that would represent 4 electrons, and the triple bond would represent that 6 electrons. There is a little shortcut I like to do here actually. Go ahead and take your shared electrons. Let me just clean this up. The 6 electrons, and divide that by 2. And that's going to tell me how many bonds. And the reason that works is because a bond always has 2 electrons in it. So single has 2, double has 4, and so on. So if I divide that by 2, I get the number of bonds. So I know it's not in the steps, but it kind of translates easier. So I've got my triple bond. Then at the end, we still need to meet our octet. So if this is 6, we still need 2 more on each of these atoms. And notice you get the same exact structure. So I don't care which way you do it, whether you're able to just count up make the sketch and count it up and make sure it matches the valence electrons, or whether you want to calculate needed, available, shared, and then be able to add your dots. They're both going to get you to the exact same Lewis structure. There's one valid Lewis structure that I'm looking for. All right. So that is method 2 of finding our Lewis structure. All right. So let's do a few more examples, and these are all going to have a charge. So I want to see how that plays into things. So I'm going to keep going with needed, available, shared, just so you get the hang of things. I'm going to work these red ones on the video, and then if you want to walk through some of the others, we can do that in class. All right, so CO2 would have a 2- charge. So first I'm going to do needed. Carbon would need 8, and the oxygen would need 8. The charge is going to affect the available electrons, but it doesn't change the octet rule, right? So again here, 8 plus 8, I have 16. Available, carbon in column 4 has 4 valence electrons, whereas oxygen has 6, being in column 16. I'm also going to include the charge. So if I have a -2 charge, that would mean I have an extra 2 electrons available. So now it's actually 4 plus 6 plus 2. So this ion has 2 more electrons than just the carbon monoxide molecule. So I have 12. So now I'm going to find the difference here, the number of shared electrons. 6 minus 12 is 4. And if I cut that in half, I can get the number of bonds, 2 bonds. So if I only have 2 atoms, that means it must have a double bond. So that double bond would represent 4 electrons. So I would need how many more then to get up to 8? I would need 2 more lone pairs, or a total of 4 more electrons on each. 2, 4, plus the 4 is 8. 2, 4, plus the 4 is 8. I have my octet. And 2, 4, 6, 8, 10, 12. I've met my budget. One thing you want to do differently when you have ions is you want to put them in either brackets or parentheses and then keep the charge on the outside. So you want to show that that molecule, or ion I should say, has that charge. That charge, by the way, is what we call delocalized, or spread out throughout the atom. It's not that the carbon or the oxygen is negative, it's that the entire ion is negative. It kind of shares that negative charge. All right, let's move on to the hydroxide. With the hydroxide, I have a hydrogen, so I've got to be really careful with the needed. Oxygen, being not hydrogen, would need 8. However, hydrogen, being hydrogen, only needs 2. So that's 10. For the available electrons, oxygen being in the 16th column has 6, and then hydrogen being in the first column only has 1 valence electron. Notice how 6 plus 1 is 7. If you ever get an odd number for available, you probably forgot your charge. So that's a common mistake. So 6 plus 1 is 7, but there's also an extra one available from that charge. So that's going to be a total of 8. So 10 minus 8, I have 2 shared electrons. And if I cut that in half, that tells me I only have 1 bond in the molecule. So I'm going to draw my sketch of the O and the H. And the single bond is going to be that 1 bond. So that's all I need. The oxygen wants 8, has 2, so needs 6 more. Whereas the hydrogen only wants 2, which it has. So there I'm done. Let's do parentheses for this one because you're going to see it both ways. So the OH has the -1 charge on the outside. All right, let's try nitrate. NO3 1-. All right. Both are not are not hydrogen, so they need 8. What you've got to consider with this is a subscript. This is our first one we're doing here with the subscript. So needed is 8 for the nitrogen, but it's also 8 for each oxygen. So it's going to be 1, 2, 3 more 8s. So 8 4 times would be 32. Now let's look at available. The nitrogen, being in column 15, would have 5 valence electrons, whereas the oxygen, being in group 16, has 6. But just like we did up here, we're going to mark that 3 times. 6, 6, 6. And then don't forget with your available to include your charge. So that's going to be 1 more. So I have 5, 3 6s, and a 1. That's going to equal 24 electrons. Now I want to subtract those for my shared electrons. 32 minus 24 is going to be 8. So I need 8 electrons in a bond. I'm going to go ahead and cut that in half so I get the number of bonds. 4 total bonds in this molecule. Now let's look at this sketch. Whenever you have multiple atoms, you're going to surround the first atom. So we'll put nitrogen in the middle and then 1, 2, 3 connections to oxygen. That's going to take up 3 bonds right there, but I need 4. It doesn't matter which oxygen I pick, but I need to put another bond in there. Molecules are real, right? They rotate, they move around. So if you drew it somewhere else, that'd be fine. It'd just be like you doing a headstand. Like it rotates, it's fine. So we've got 2 electrons added to one of the oxygens. You do have to be careful here about your octet though. This would represent 4 total electrons. So the oxygen with the double bond would only need 4 more. So it would have 2 lone pairs or 4 electrons. Whereas the oxygens with the single bonds only have access to 2 in the bond. So they're going to need 6 more. 1, 2, 3, 4, 5, 6. I'm going to do the same to both oxygens that have the single bonds. And also look at nitrogen. A lot of people forget to think about the central atom. Does nitrogen need any more dots? Well, it has 2, 4 here, then 6, then 8. So just in the bonds that it's sharing, it already has access to 8. So no more electrons on the nitrogen. So this is going to complete nitrate with the -1 charge. All right, so these next couple are going to be very similar. Again, we can go over them in class. I'll show you the answers in just a minute, but just kind of trying to keep the video short. Let's skip over here to the NH4 so we can do one with a positive charge. So let's do needed, available, shared. Needed for nitrogen is going to be 8, but the hydrogen, remember, was the exception, only needing 2. But you're going to have that happen 4 times. So I'm going to write down 4 2s to represent the 4 hydrogens. So 8, 9, 10, 11, 12, 13, 14, 15, 16. I need 16 electrons for my octet. What about being available? So the nitrogen, how many valence electrons? Well, it's in column 15. Available. So it would have 5 valence electrons. And then the hydrogen, being in the first column, would have 1 electron each. So I'm going to have 1, 4 times. 1, 2, 3, 4 to represent the 4 hydrogens. Now let's think about the charge. We always have to think about the charge with the available electrons, because that affects our budget, right? If having negative charges added extra electrons, since electrons are negative, what do you think having a positive charge would do? Well, that would have to mean we've lost electrons. Remember, you can't change the number of protons? So the positive charge has to come from the number of electrons being lost. So I'm actually going to take one away, or you can erase one of those plus ones. I'm going to take away 1 from the net. So I've got 5 plus 1 4 times, but then minus 1 because of that positive charge. So we actually have 5, 6, 7, 8, 9, but then minus 1 would be back to 8. I actually have only 8 electrons available. So 16 minus 8 is 8, which I will then cut in half to give me the number of bonds, 4 bonds. So when I sketch this out, let me actually do it up here so that we have some room. Nitrogen with 4 hydrogens around it. In order to connect each of the hydrogens, I need 4 single bonds. Well, the molecule is only supposed to have 4 single bonds. So that's it. That's the end of the molecule. Now let's check our octet. The nitrogen has access to 4 single bonds. So if each bond has 2, that would be a total of 8 electrons available for the nitrogen, and so we're done. Hydrogen only wanted access to 2. So if it has access to a single bond, that's all it needs. So that means we're not going to put any dots on the hydrogen either. So now all that's left is to put the charge on the outside. So that would be the correct Lewis structure for the ammonium ion, or NH4+. All right, guys, the next video that we're going to look at is going to take these Lewis structures, and then we're going to build on that, and we're going to figure out how electronegativity plays a part in their polarity, and we're going to look at how their shape is determined by these electrons. So you're looking for Unit 3, Note C. We'll see you there.